Hi, everyone. All right, let's talk a little bit about a little bit of the history of black holes. Some people think this is a new idea, and it's not. They have been theorized way back in the 1800s. John Mitchell and Pierre-Simon Laplante, based on the gravitational equations of Sir Isaac Newton, they were thinking about this way back in the 1800s. A gentleman named Carl Schwarzchild did the math based on general relativity way back in the 1916. So for well over 100 years, people have been imagining black holes and their existence. Mid of the last century, 1958, David Finkelstein came up with this idea that it's a possibility to have a region of space that is so dense, the gravity is so intense that nothing, not even light, could escape. By the 1960s, neutron stars were discovered, and that is that work of Kent Ford and Jocelyn Bell. Then by 1968, John Wheeler, the American physicist, was the first person to actually use the word black hole. And it was such a wonderful name that it caught the psyche of the popular culture and physicists and astronomers around the world. By 1975, Cygnus X1 was observed and was believed to be a black hole because of the gravitational effects it was having on companion stars. By the year 1990, Cygnus X1 and its effects were observed with enough detail that it was very well accepted in the astronomical community that this was a black hole. Now, that was 30 years ago. So for 30 years or so, we have agreed that black holes have existed, but we have not had an awful lot of proof. By 1995, people were starting to photograph the effects of these black holes in the center of our Milky Way. What were they doing? How were they making other stars orbit around what appeared to be nothing there, but black holes were seen? In 2015, gravity waves were detected, and we will spend some time talking about gravity waves this chapter. And that was a big deal because we think collisions of black holes are one of the ways that gravitational waves can be produced. And in 2019, huge event in the history of astronomy, the very first black hole was actually photographed. And this is a picture of that first photograph of a black hole. It was made in April 2019. This is the heart of not our galaxy, but is the M87 galaxy. And it is 50 million light years away just due to its location in the sky. It was a nice clear black hole in the middle of this galaxy that astronomers were able to picture. Now, they had to do this using radio telescopes, and radio telescopes have the wavelengths that are long enough to penetrate through the dust and the debris that is surrounding and swirling around the center of a galaxy. They had to have, because they had to use really long wavelength radio waves, they had to have a big telescope. How wide? Well, about as wide as the Earth. Well, we don't have telescopes that big. So what they did is they connected 7 Earth telescopes to create a virtual telescope. They connected electronically telescopes from all over the planet, many, many years of data, collecting that data, cleaning up the data, taking out stray signals from dust and debris and other things. And this is that picture of a black hole. So all other images that I have floating through my notes are actually artists' drawings. And vast majority of the simulations, unless it's this picture or something newer than this April 2019 image of a black hole, are actually artist drawings of black holes. They are very, very rare. We are so used to these artist renderings that we have a tendency to think, oh yeah, we have lots of pictures of black holes, but we do not. This was the very first one that was taken. Now, one of the terms that you hear in a lot of science fiction movies, etc., is the event horizon. The event horizon is this area where there is the point of no return. There was a gentleman named Schwarzchild, early 1900s, and he did the math. The Schwarzchild radius is the radius of the collapsing star where the math says no light can escape. And the surface of this radius, this actual distance, that is called the event horizon. Now, one of the things I want you to be aware of is in movies and in a lot of illustrations, and even when I draw black holes, we have a tendency to draw them as if they are a funnel or a disk. But this is actually a sphere. This is a round area. And around this area, it is usually in images very, 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 very bright because of the fact that there is a lot of energy as objects are, debris, matter is swirling into the center of this black hole. It is giving off lots of gamma radiation, X-ray radiation, as it is plummeting into this gravitational abyss. But that event horizon is the edge, and the radius of where that point of no return is called the Schwarzchild Radius. Now, there is a simple mathematical relationship here. For each solar mass, multiply that times 3 kilometers, and 3 kilometers is somewhere in the neighborhood of about 2 miles. It's not exactly that, but it kind of gives you the ballpark figure. And that will tell you the size of the event horizon. So if our sun was a black hole, 1 solar mass, the event horizon around it would be 2 miles. So it would not be a monumental thing to travel around, okay? It would not be such a huge thing that we couldn't move around it if we knew where it was in outer space. We could certainly drive around it in our spacecraft. But as black holes get bigger and bigger and bigger, and super gigantic black holes, the event horizons have a tendency to get larger. So if you have something that is 100 solar masses, 100 times 3, you're going to have a 300 kilometer or a 200 mile across event horizon. Again, that is not that massive. But when you start having black holes that are millions of solar masses, well, multiply that by 3, and all of a sudden you've got something that is maybe 6 million kilometers across or 4 million miles across. And now it's something that you definitely have to watch out for, and definitely don't want to fall in, because that is the point where if you do go in, the gravitational tug is so huge, not even light can escape. Now, what is at the bottom of a black hole? Anything that does fall in. Astronomers talk about something, or physicists talk about something, which is referred to as a singularity. A singularity is a term that is used in mathematics. It is kind of the word means a point with 0 radius. So if I draw a dot on the page, that has a height and that has a width. If it was a real dot done with ink, it would also have a height. There's a certain amount of ink there, and you could measure the height, width, and depth of that spot. Well, a singularity is a point that is so small that it has no height, no width, and no depth. And the idea is that the center of a black hole could be so small, gravity could be so incredibly intense that it would pull things down to a singularity, an infinitely small point. And that is what classical physics says. Well, the early 1900s, there was a thing that was discovered, or that nature does, and it is referred to as quantum mechanics. Quantum mechanics is the physics of the very small. And on the tiny quantum level, it is discovered that the neutrons that make up atoms, protons, neutrons, and electrons, the neutrons, have actually a degenerative force. You can only squeeze them down so much when they are going to say, nope, no further, and they start pushing back a little bit. This is called the neutron degenerative force, and that will stop the collapse. So we believe in reality it doesn't go down to a perfect singularity, but it will go down to something very, very small, and it will possibly stop existing between normal space and time. So if a black hole if this is a curvature of the fabric of space-time, maybe it curves space-time so much that it may actually rupture the fabric of space and time. All right, that will do for this one, and we'll come back next time and talk about some other weird and wacky stuff. See you then.